Thank you very much. I'm so interested to exchange some ideas with you about how to increase additive manufacturing with powder. As a national lab, we have a very strong initiative related with that, so maybe it's necessary to share some ideas. The presentation was magnificent about how the results making small changes about the process are so necessary. Sorry about that, that comment. Hi, my name is Leopoldo Ruiz. I'm the head of the National Lab of Additive and Digital Manufacturing in Mexico. This national lab is integrated by high-level institutions like Tecnológico de Monterrey, UNAM, Autónoma de Nuevo León, and many others. And this presentation is brief and is incomplete presentation related to how to design for 4D additive manufacturing. It's for us, it's very interesting to ask the question how to design for 4D additive manufacturing, because we are experimenting exactly the same problems for 3D additive manufacturing. It means material, processes, and geometries are the key in terms of obtaining the performance that we are looking for. So this is a very simple presentation. What is 4D additive manufacturing, how to achieve 4D additive manufacturing, some applications and some conclusions. But the end of the presentation is more related with the problem statement associated with how to design, included for 3D and 3D additive manufacturing. So of course that it's everyone in this room and connected online know very well what is 3D manufacturing or 3D additive manufacturing. And this is, I don't know, this is a pointer also? Yes, oh, great. This area, which is related with material, process, and geometry, that depends on how to keep the intersection of this. Oops, where is the laser? Well, let's think that the intersection between material, geometry, and process, this is a sweet spot related with performance. But the main idea is how to keep this performance across the time. Specific for polymers, they are or could be changing across the time depending on the operation conditions. So the 4D additive manufacturing just includes how to apply, or which is the response that you obtain when you are applying a specific stimuli for a particular component. It means how this component is going to change the properties, the shape, or the performance that you are thinking about when you are applying a specific not operational condition plus and stimuli. So we are talking about performance, but we are talking about the response. And the main idea is how to keep or how to take advantage of this response specific or depending on the operational condition, of course, and the stimuli. And this main idea that it's very ancient in terms of academic proposals has several names. 4D printing, of course. Everyone knows very well that I have some issues when we are using the word printing, because not all the process has a specific head, and not all the process include specific materials related with printing. In my opinion, we must to be more fundamental and use the term additive manufacturing, which is the right one. And of course that other terms like shape-shifting structures and design for function and many others has synonyms in terms of this developed related with 4D additive manufacturing. Why is important to use 4D additive manufacturing? Of course that it's possible to change the shape of something, and maybe this is the most common idea when we're talking about 4D additive manufacturing, because think, for example, for healthcare applications, it's very simple to introduce something in a small size, and it's possible to increase the size inside of the body without minimum chirurgical issues for the body. So it's, Another way is that it's possible to modify the performance, the properties of a specific components when we are using a specific stimuli. It means it's possible to allocate small parts or small additional material for a matrix and modify the rigidity of something, or modify how to most to deform when you are using a specific condition. So let's chat a little bit specific for polymers, but I insist that this is going to be a play for different kind of materials, included ceramics and metals. But if we are using the specific for polymers, it's possible to think about how to program the formation, how to program the response that a specific component is going to have. So for polymers, of course, that it's, oops, I really have an issue with that. I cannot see the laser, okay. It's possible to have the original polymer. It's possible to apply some temperature in terms before to the formation, and it's possible to cool in the material, and then it's possible to apply a specific temperature. In that case is the TG temperature, the transition temperature, and it's very simple to modify the performance or to change the shape of this material. So, of course, that there are different results that it's possible to find with this idea. It's possible to build something. This is the simplest way of this 4D response. It's possible to build something, apply a specific temperature, and the shape is going to modify the structure or the rigidity of this component. The second one could be to use a specific pre-programming about the shape using heat and cooling process, and then it's possible to move across the deformated component to the original shape. And this is only one way actuation of this component. But the real or the most attractive area is when we are talking about the reversible way of these components. It means it's possible to apply a specific programming for a material, for a component, and then use a stimuli to modify the shape or the properties, and then it's possible to use another stimuli to modify or change the response of this material. So it's very interesting because in terms of design, we are thinking in the same component to include the sensor and the actuator. So it's very, very interesting how to reduce the number or the amount of components on a system. That's why it's so relevant in terms of why 4D additive manufacturing is gonna growing up so fast in terms of applications. And of course, that depending on the stimuli response, it's possible to think how to modify, how to use a specific stimuli, in that case, heating, cooling, and then the total deformation, and how to take advantage not only in terms of the amount of components. We are talking about how to have a specific response with the material is under operational conditions. It means it's gonna possible to design something for the aerospace industry, that the conditions are so different than on Earth, and then it's possible to use this kind of responses. But the way to obtain the response of the 4D components, of course, that could be to use not only the geometry, not only the specific material. It's possible to modify using multiple materials. And the specific sandwich structure or multiple material structure are studied today. This is a multi-jet machine, and it's possible to allocate different materials, and depending on the areas that you're allocating this kind of materials, it's possible to obtain different kind of responses. But of course, that depending on the materials that it's going to be, sorry about that. Depending on the materials that, okay, there we go. Depending on the materials that we are using, it's possible to identify different kind of applications, different kind of structures, shapes, and responses. And this is maybe the most attractive area in our opinion, because it's the simplest way to obtain the response. It means to modify the shape or the design that it's commonly named the design, but we're talking about geometry, how to have specific structures that it's possible to modify all the across area. For example, when we are using sensors like flow sensors, it's possible to modify the response or the shape of these materials depending on the stimuli that it's going to be applied. And in this field, we have temperature, we have ultrasonic applications, magnetics, and so on. So, of course, that the process modified the response that it's possible to find depending on the process parameters used. For example, this author identified that the deposition speed increases the amount of the characteristic of the deformation depending on the material that he is using. So it's going to give us an idea how not only the material, not only the stimuli, not only the shape, is going to give us a specific response. And this catalog, it's very interesting, depending on how it's possible to obtain, depending on the combination of different kinds of materials, and depending on the process that we are using, and of course, that the geometry that was applied, the result that it's possible to find. So let's think not only in the possible applications of that. It's possible to think in bio, specifically for bio and fold care. This is very attractive for the project that we were chatting before, a couple of hours, related with how to have a specific response when we are using anatomical structures. It means almost everything inside of the body has a specific motion, digestive system and cardiovascular system has a specific response. So it's possible to develop structures that is going to have motion depending on the stimulus that is going to be applied. But let's think in organs. It means it's possible to have, this is a major idea, and I guess that every one of us, it's a dream, only a dream at this point. But of course that it's possible to think in the future to use or to develop specific organs in terms to using exactly the same stimulus that right now the body is using. So let's gonna move from a very simple material, PLA material, it's very simple, very cheaper, and very common today for systems for material extrusion. It means filaments. So it's very simple to identify that this material that is really, really cheap is going to give us a specific response depending, of course, on the geometry, depending on the temperature that it's going to be applied, the stimuli, and depending, of course, of the programming process that it's going to have. So many authors are studied about, was studied about the response of these kind of devices, and the idea to use very ancient ideas related with design, like origami design and many others, is going to give us a specific area to obtain the response. It means in this area, the size of the amount of materials allocated in these points is going to diminish, so it's possible to obtain motion in this area. And of course, that it's going to give us an idea how to decrease the assembly, the number of components related with that, and how to take advantage of these kind of ideas. For example, for reduce the amount of components, not only in laboratory, we are talking about the industrial components, because if we modify the amount of materials allocated in a specific area, it's going to change the performance, it's going to change the, of course, the mechanical response, the magnetic response, and of course, the deformation that it's going to be obtained with that. So the idea to use these simple parameters, material process parameters, and of course, the geometry used for that, it's take relevance when we're talking about how to modify the response of that idea. And one of the biggest applications with that is going to have these kind of devices, grippers, because it's very simple to use exactly the or not. Yes. It's very simple how to use simple structures that is going to modify the actuation over a specific material that is going to be adapted in terms to keep safer the load over the gripper. So just to close this brief presentation related with the design for 4D additive manufacturing, we chat about the material, we chat about the process, and we chat about the geometry, but of course that it's necessary if we are thinking in production to think about the production volume, the logistic, the reliability, and the performance related with that processes. So it's not a simple task only to think in laboratory applications, of course, related with 4D additive manufacturing. It's very important to think how to expand the application of that kind of devices, depending on the amount of production that we are talking about, depending on the kind of technology, and depending on the kind of materials that is used. So those are some ideas related to how to design for 4D additive manufacturing, but at exactly the same problem when we are talking in 3D additive manufacturing. So this is the end of the presentation, and I'm so open if you have any questions related with that. Thank you very much.
Thank you very much, Dr. Ruiz.
My pleasure.
Someone has any question for Dr. Ruiz? Over there. Thank you.
Can you help me, sorry, we're over here. Can you help us understand time scale? So for instance, the stent example, I would want to maybe open over a day or hours, whereas a gripper, a day worth of translation would not be acceptable. So like maybe can you tailor the response times and maybe what some strategies are to kind of optimize an application-specific, time-based dependency?
Yeah, and specific with metals or in general terms you're talking about?
Look, I suppose we'll go general. And that's a harder answer, but.
Yeah, because that depends where, for example, taken in a very simple manner, it's possible to think, for example, grippers that change the response in terms of hydrophilic response. It's possible to have the device underwater, you move the gripper, then the gripper is going to close, and automatically the gripper is going to take this device. So it's possible to move on and then take another place for these kind of devices. So trying to answer your question, it's very interesting how to think the real applications, the real condition, and the stimuli that you are planning to use in terms to find the response of this kind of devices. So this is in general in terms one of the way to try to solve that.
Thank you very much. Another question for Dr. Ruiz? Over there. Thank you.
Hi, the biomedical applications were really interesting, and while some part you have to take in account like the biomechanical part, as you said, like the algorithm, but also to insert it into the body, you have to think of the cells that are going to interact within there. So I don't know if within the institute you also take in account like the cytotoxicity that will count it, because sometimes to have like kind of the reaction with the temperature. Like I used to use NIPAM, and that one caused some cytotoxicity. So the question is that if in this institute are you looking for some additives that are or bioinks that can be less harmful to the cells?
The position of cells. Yeah, this is a very interesting question related with this issue. Not all the processes are ready to use for cells, of course, and not all the stimuli are prepared to work with bio applications. Temperature is very common for industrial applications, but specific to try to work with temperature in terms of the biological applications. There is a real issue. Small changes on temperature is going to kill some cells. So it's very important how to keep on track the real conditions, the limits of that conditions, and which could be the real stimuli that it's going to apply. For example, for bio applications, a lot of electrical stimuli is going to working better because we are trying to keep alive this kind of cells and this kind of motion and this kind of response about that. So it's difficult to have a general answer without the specific case, but of course that how to keep alive this kind of cells is one of the biggest challenges, one of the biggest specifications where you are doing this kind of design.
Thank you.
Thank you very much. Another question over here, the last one.
Yeah, thank you, Dr. Leopoldo, for this amazing presentation. I was wondering regarding this stimuli-responsive additive manufacturing, what are your thoughts on, if there are some, actually on the limitations that this technology has for actual applications like the latter that you mentioned on the PLA grippers, related to how much actually it can deform and the force applied?
Very, very tough question. The limitations, all of them, sorry, because right now there is not commercial in my as the best as I know. There are no really applications related with 4D additive manufacturing in terms of gripper. So the idea is how to move only a laboratory idea, how to move that to industrial application. So in terms of the results that we have inside of the laboratory, for example, we are programming PLA with a compression stimuli, and it's possible to decrease almost the half of the height of this device, and it's possible to recover almost the 80% of that. If you say, oh, come on, this is only the 80%, this is a good or not efficiency in terms of if that kind of accumulated force is going to be used for a specific application. So for some task that we are trying to apply, that is not good enough to have this kind of deformation and this kind of recovery of energy and motion. But for other applications, and one of them very simple, it's possible to start moving something specific for a small actuation area, and it's good enough. So the first results that we have inside of the lab start many ideas related that this is, of course, not only the material. We are talking about how to design this kind of specific areas in terms to increase the recovery, the energy recovery on that. But when we applied a lattice structure for that kind of structures, we have done a better motion, a better recovery, but less energy, less accumulated energy. So there is a mix between that. So right now, this is only exploring the field, but I hope that, I don't know, maybe in a couple of months with the experiments that we are running right now, I'm gonna give a better answer related with that. But at this point, the limitations, all of them, because it depends too much of a lot of parameters. The people who works with material extrusion with filaments identify that it's possible to modify at least 20 parameters, starting with temperature, diameter, flowing, and the number of geometries are unlimited. So it's going to be difficult talking about only one material. So it's a hard topic at this point, but of course that it's achievable to find a set of parameters and a set of conditions that give us a better result. My pleasure.
Thank you very much, Dr. Ruiz, for your excellent presentation.
Thank you so much.